Hello everybody. Today we'll be talking about fluid dynamics, viscous fluid flow, and Poisson's law. We started talking about fluid dynamics last week, and we introduced viscosity, and now we're going to have some equations. So, as a reminder, Bernoulli's equation was the one that enabled us to be able to figure out things like the velocity, and the pressure at different locations in some pipes. Okay, so let's say we have a pipe going uphill or downhill, changing in diameter, radius, or area. Knowing enough information, we can figure out what the velocity and the pressure is everywhere. So the problem was resolved by an energy approach, right? So what we have is the work done is the force times the distance, and so we've got this difference from one point to the other, and we've got the difference in the energies, which is the potential and the kinetic energy. And look, it's really just important to get an idea of that's where this came from. And what Bernoulli gave us was this equation that said at any point along the tube, we've got the pressure plus the rho gy plus the 1/2 rho v squared is a constant. I'm going to remind you that the way you deal with these problems is you pick a reference height. You know, it could be sea level, it could be whatever, okay? In fact, I'll tell you something. Very often, the most convenient reference height would be right here. Why don't we just choose this instead? We're going to say h is equal to 0, you see? And so, in this case, y1 would be equal to 0. Hey, that's nifty, okay? And then all we would have to do is take on this difference. Now, another point I want to make is that you see when you have this tube, you don't measure the top of the tube, the bottom of the tube, it's the middle of the tube, okay? We ignore the fact that there are different heights within the tube. It's just the center. We're measuring from the center line, okay? Move on. So here at the bottom, that's how you're going to be using this equation, okay? We've got two different points, 1 and 2. The trio on the left has to be equal to the trio on the right. Typically, things cancel. Lots of things cancel right away. So recap, we've got the continuity equation, which says that the flow rate stays the same everywhere along a tube. Doesn't matter whether the tube is getting wide or narrow, going up or down. This equation works, and it's a relationship between the flow rate is equal to the area times the velocity. Okay, and then you've got Bernoulli's equation, which this is how you use it: point A versus point B, and this all works for ideal fluids. Okay, ideal fluids are fluids that aren't in turbulence. Okay, first of all, but they're also don't have any viscosity. So remember, we did this problem, and this is in the notes. You've got a constriction. There's no viscosity given in the problem. We know that this has to be a Bernoulli equation problem. The continuity equation says area 1, velocity 1 is equal to area 2, velocity 2. That gives us a relationship between the velocities. Here, I've done it out. So you've got Bernoulli's equation also, because the height is not changing. Okay? You write down Bernoulli's equation, and the first thing you do is you cancel out the two potential energy terms. Okay? Then we can use the fact that they told us the volume flow rate, and they told us the radius or the diameter. We were able to figure out the velocity, 1. So now we know the velocity, okay? I'm going to draw a circle around it. We know this. Check. Okay. Obviously, we know density. What else do we know? We know that they said that the pressure dropped by 40 Pascal. So we're going to plug that in there. I'm going to write it out. P1 plus 1/2 rho V1 squared is equal to P1 minus 40 plus 1/2 rho V2 squared. Okay, so now we can cancel these out. Don't lose track of this minus sign. Okay, minus signs are a killer in this type of problem. You keep track of the minus signs, you'll do great. Okay, so we know now V1, we know density, we can solve for V2. V2 squared would be equal to what? 1/2 rho V1 squared plus 40. And then I can throw more things to the right side. And we get V1 squared plus, multiply everything by 2, right? To get rid of the half, 80 over rho. Okay? And then if you want, you can say V2 is equal to square root of V1 squared plus 80 over 1,000. Right? I just plugged in the density. And actually we know V1. Why don't I say 0.14 squared. Okay? And so then you'd plug that in. So that's all done here. And you work this out and you'll get that once you figure out the velocities, you use this flow rate equation that I've written over, and you get the 2 millimeter diameter. Okay, so that's a classic problem. Now there was this one that I introduced last week, and I pointed out this in the textbook, and it's complicated. I don't want to dwell on it, but I have I did a nice graph over here, so I wanted to show you. The idea was that you needed to figure out what the pressure was in an intermediate point. They gave us the area at one end of this tubing, the other end of the tubing, and we needed to figure it out here in the middle. Okay, and that's where we did the equation of the line and figured out the point. We move on. Okay, so that's Bernoulli's equation. And then we talk about viscosity. Viscosity is what makes thick liquids act like thick liquids. Okay, that's what distinguishes, let's say, something like milk, molasses, milkshake, shampoo, peanut butter versus water. Okay, I mean, actually, you can, in some cases, have to consider even the viscosity of water. Okay, but what I'm saying is that the viscosity is the characteristic that describes these differences, okay, between what we could call a thick liquid versus a thin liquid, okay? So ideal fluids don't have viscosity. We ignore the viscosity, okay? So then you could talk about the units of viscosity. But what I want to get to is, okay, in equations, okay, that we're going to use. I pointed out last week that when you have viscous flow, you're going to have sort of a drag. So what happens is the if you've got 5 people floating down a river, just following the water flow, right? What you might find is that the water is going to be slower at the borders, okay, because it's getting a drag. It's getting brushed up against something that's standing still. See, and then the second one over here is sandwiched between, okay, a slow flow and a faster flow, but the fastest one is going to be right down the middle. Okay, so that's something to understand, and that's going to happen in rivers, and that's going to happen in arteries and veins. okay? Capillaries inside your blood system. We'll talk about that later. Viscous fluid flow, okay? Now, this is a very important equation. It's called PHYS law, okay? PHYS law relates the flow through the tube, okay, to these variables. Now, R is the radius of the tube. Delta P is the pressure difference from one end to the other of the tube. L is the length, and eta is the viscosity of the fluid. So I'm going to show you a picture of how you use it, okay? But before I do, I want to point out that often, okay, people will describe the situation with what's called pressure gradient. So what they do is, pressure gradient is a very useful parameter. It's delta P over L. It's the difference in pressure divided by the length. Okay, so now how are we going to use this? So we have a tube. It's going to be a horizontal tube, always. Okay, we're not going up and down, anything like that. It's going to have a radius R. It's going to have a length L. Okay, there's going to be a difference in pressure as well from one end to the other. Delta P. Okay, so delta P is equal to P in minus P out. Okay, that's what it is. So is there anything else? No, there's the radius and the length. Those are the geometric parameters that describe it. Delta P is the pressure difference from one end to the other, and Q is the flow rate. So in reality, what this is saying, look at the bottom equation, it's pointing out that if you don't have any pressure difference from one end to the other, you're not going to have any flow. Okay? So if you're just thinking about sucking, let's just say you have a straw full of a milkshake and it's really thick, and you've got to do some work. You've got to suck on that, and you have got to have a lower pressure, right, on your side versus the atmosphere at the other end of the straw for it to go into your mouth. That's even if the straw is horizontal. We're not even talking about up and down. We're just talking about a horizontal straw full of peanut butter or milkshake or whatever. This is the mathematics that tells you how much pressure it's going to take to suck that stuff into your mouth. Okay, so you've got a straw. Wait. Let me see if I can do this. Okay. It's not me, okay? Why is that me? Okay, maybe it was me long ago. Okay. Okay. There's going to be the P. Now it's flowing this way. So this would be the P in, and this would be the P out pressure, right? What really counts is it's the delta P, okay? And you've got a difference in length of the straw, and there's going to be the radius, okay? Let's keep on going. So that's to get this stuff going in, okay? Next, well, that's R. And of course, someone would have to give you the viscosity of the fluid. Let's move on. We're going to do a real problem. So, wait, I'm going to pause it, and I'm going to record this in the next part.